So we're going to just continue on our discussion about um, energy. I'm going to talk about potential energy now. So potential energy is the energy that an object has because of its position or structure, not its movement. So its best way is down the bottom there where it says it can be called stored energy. So stored energy is sort of sitting there. It's waiting to do something. It has a potential to do something, but something needs to happen before that potential can be realized. In other words, that energy can be transformed into something that can do something useful for us. So chemicals in foods and explosives contain energy in their chemical bonds. It's the same way as fuel in our cars has potential energy in the fuel. Okay, so it's stored energy. So elastic potential energy. So a stretched or compressed spring or elastic material has elastic potential energy. It is converted into kinetic energy when the spring is released or it returns to its original shape. So some examples of elastic potential energy are springs on trampolines, car bumpers, bungee cords, slingshots, mouse traps, because they've got that spring and that trap. And when the mouse touches that little lever, that energy of impact that the mouse gets that kills it or traps it is stored in that spring. So that's what we call stored energy. So gravitational potential energy, an object positioned above the ground has gravitational potential energy, like something in a tree branch. Gravitational potential energy can be calculated using this equation here. So potential energy equals mgh, where m is the mass, g is our acceleration due to gravity, our 9.8 meters per second, which we've talked about before, and h is the height above ground in meters. Always got to be in meters because meters is the standard international unit. A little worked example here. Sarah is 6 years old and has a mass of 30 kilograms. Again, notice we didn't say she had a weight of 30 kilograms. She has a mass of 30 kilograms. Calculate Sarah's gravitational potential energy. A, when she climbs 2 meters up a vertical ladder to the top of a slide, and B, at the bottom of the slide. So A, the potential energy is just our formula mgh. So m is a 30 times 9.8 times 2, because she's 2 meters above the ground, and that comes to 588 joules. So Sarah's gravitational potential energy at the top of the slide is 588 joules. At the base of the slide, Sarah's height above the ground is 0, and so her gravitational potential energy is 0. The question now is, where did that energy go? We know energy can't be created or destroyed, so where did that energy go? What's happened to it? So here's your turn. You want you to calculate the gravitational potential energy of a half a kilo bird flying 20 meters above the ground, a 20,000 kilogram helicopter hovering 300 meters above the ground, and a 2 kilogram money box sitting on a bookshelf at the height of 2 meters. Okay, if you want to just turn the video clip off, the YouTube clip off, have a go at those and come back and we'll see if we can work through the answers together. Okay, the first one here, our potential energy here is just 0.5 because that's its mass times 9.8 times 20. Okay, and that comes to 98 joules of potential energy. So that bird flying has 98 joules of gravitational potential energy. It also has a kinetic energy as well, which we could add to that, but at this stage we just want its gravitational potential energy, and that's how we work it out. For the next one, it's going to be a lot bigger because we've got a big, massive object, and it's very high up in the air. And so we put all calculations in, and by my calculating, that's 58.8 megajoules. So that's a lot of energy there. So a lot of potential. And imagine that's a lot of energy if that helicopter suddenly fell out of the air. Now, that would be the energy of impact there, the one that hits the ground. That's a lot of energy. Last one, the little 2 kilogram money box is 2 times 9.8 times 2 which equals 39.2 joules. So this is its potential energy. And of course, if you were on the floor, if that fell to the floor, that's how much kinetic energy it would have just as it hits the floor. And that'll help us with the next question. Okay, hopefully you got those correct. We'll move on. So the law of conservation of energy. Energy may be transferred from one object to another, but it's never created or destroyed. Energy may also be transformed from one form to another. For any situation in which energy is transferred between objects, there is always the same amount of energy at the end as there was at the start. The total energy involved in the system remains constant. We can express this by stating the total energy equals the potential energy plus the kinetic. Okay. Now I've got the idea of transferring energy versus transforming. A transformation of energy refers to the changing of energy from one type to another. For example, an electrical motor changes electrical energy into mechanical energy. But of course, it only changes it. It doesn't create it or destroy it. It just moves it around, if you like, or changes it to one form, but it's exactly the same amount. Now, some is lost, but we've got to be careful when we use the word lost. But we'll talk about that when we get to efficiency a bit later. Now, transfer refers to the transfer of one energy from one object or place to another. That's like heat transferring from a hot plate to a saucepan. It still is heat energy in both cases, but it's gone from one object to another via heat conduction. Okay, we'll quickly talk about systems. In systems, we have the concept of the law of conservation energy relates to the idea of a system. A system is a connected set of resources and processes. A simple system is composed of three parts: the input, the processes, and the outputs. So we'll just have a little talk about that. Go to the next slide when I can work out how to get down to the next slide. There you go. Sorry about that. So inputs, processes, and outputs. A system may be part of a larger system, with the universe being the largest system of all. The three levels of systems are the local systems, comprising the components immediate to us, surrounding systems, the area immediately outside the local system, and the universe, that's everything else. So what does it all mean? On the universal level, the energy is conserved. However, at the local system level, the energy transfer and transformation processes lead to less energy being available at the end than at the beginning. Okay, this is what we've got to remember. We're still not creating or destroying energy. It's energy moving in and out of a system. In an energy transfer or transformation process within a local system, some energy is always transferred or transformed into the surrounding system. That's talking about losing energy through friction and through heat and sound as well. So yeah, we'll talk about that when we get to efficiency. I'm going to talk a little bit about impact here in crumple zones. There's a classic example of a crash test that's been done. So you see the car having a full-on impact there. And you can see the airbags there have been deployed, and the car's crumpled up. Now the reason that actually it's good for cars to crumple up. If you want to have a little think about why crumple zones, it's good to get in an accident. Well, it's not good to get in an accident, but if you do get into a high impact accident, why it's better that your car crumple up for your sake rather than the car stay pretty much intact. So they're the crumple zones, they're the main ones. The two crumple zones are at the front and the back. You don't want your passenger section to crumple because you're sitting in there. So basically what happens with a crumple zone, it absorbs a lot of the energy of impact rather than that being transferred to you. Okay, just a quick problem here. Worked example, a 5 kilogram ball is dropped from a height of 3 meters. We want to calculate its potential energy when it's released, the total energy when it's released, kinetic energy when it's fallen halfway, and the kinetic energy when it hits the ground. So let's have a look at this. This example is for converting potential to kinetic energy. First one, we want to find out the potential energy, and we get our formula MGH. When you get the answer for this one is 14.7 joules. So that's, pardon me, that's the gravitational potential energy of that ball at a height of 3 meters. Now part B, pardon me, when released the ball has no kinetic energy. That means just at the point of release. So its total energy is 14.7 joules. Halfway, the ball is at a height of 1.5 meters and has gravitational potential energy given by this, 7.35 joules. The total energy is still 14.7, so the kinetic energy must be 14.6 take 7.35, which equals 7.35. The ball has the same amount of kinetic energy as potential energy halfway down. Part D, when it reaches the ground, there is no gravitational potential energy, so the kinetic energy is 14.7 joules. Okay, so if we note from here to here, our potential energy has been all converted to kinetic energy. Up here, Ke equaled 0, down here it equaled 14.7, up here Pe equaled 14.7, down here the potential energy is 0. Okay, we'll just stop it there and come back and finish our little talk about energy.